Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 29, 2025, about 4 days ago. It introduces a novel architecture for the internet computer that secures transaction privacy by routing transfers through short-lived, disposable intermediaries. The paper is titled, A Privacy Protocol Using Ephemeral Intermediaries and a Rank-Deficient Matrix Power Function, RDMPF. And as we'll see later, the protocol achieves sender anonymity and forward secrecy while avoiding the significant overhead typical of zero-knowledge systems. Alright, the process begins with the setup phase, detailed here. In the first step, the system publishes the necessary public parameters, including the prime modulus P, and the matrix dimension, which configure the underlying cryptographic math. Crucially, step 2 shows that Alice generates a fresh, one-time key pair for every single transfer, a design choice that prevents observers from linking her transactions together. Bob, meanwhile, keeps a stable key pair with private components lambda and omega. Finally, these public keys go into a pseudonymous registry, allowing users to find each other while keeping their real identities off the record. So, once the keys are ready, the protocol enters the spawn phase, shown here. It starts with step 1, where Alice officially requests the transfer. Crucially, in step 2, the factory spawns a completely fresh set of canisters, including intermediaries I1 and I2, and a witness W, specifically for this single transaction. Then, step 3 enforces security by making these canisters self-controlled and setting a mandatory destruction timer, ensuring nothing persists. Finally, step 7 handles the economics, where Alice prepays all fees up front to cover the life cycle of these short-lived components. Well, following the spawn mechanics, Table 1 outlines the minimal trust assumptions that underpin this architecture. The top 3 rows identify what is strictly required. The underlying ICP management canister must function correctly, and the factory code must be open source and audited. But arguably more important are the bottom rows, which indicate what is excluded. The system does not demand trust in the factory operator or individual ephemeral canisters, because clients verify the certified code hashes directly. Well, having established the trust model, Table 2 now breaks down the communication costs. The first row lists the token or key matrix, which requires about 3.4 kilobytes at dimension 12. Below that, the sealed payload adds minimal bulk, typically just 1 or 2 kilobytes for encryption overhead. This means, as shown in the bottom rows, that the total on-wire data per canister stays around 5 to 6 kilobytes, ensuring the protocol remains lightweight. Alright, while the previous table focused on byte counts, Table 3 serves as the formal glossary for the protocol's mathematical notation. The top section defines the foundational parameters, such as the prime modulus P of at least 192 bits, and the matrix dimension. The middle block details the cryptographic objects, listing Alice's one-time public key and the shared secret Z derived from the rank-deficient matrix power function. Finally, the lower section standardized the ephemeral actors, like intermediaries I1 and I2, alongside the specific algorithms used for hashing and encryption. So, wrapping up, the key takeaway is that combining ephemeral infrastructure with rank-deficient matrix power functions creates a robust privacy layer without the heavy computational cost of zero-knowledge proofs. This approach effectively neutralizes metadata leaks by ensuring no permanent record survives the transaction. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.